The charging cable running from the wall to your phone right now is about 1 meter long. Somewhere inside that cable, electrons are supposedly carrying the energy that's filling your battery. Here is the number nobody tells you. Those electrons are moving at roughly 1/10 of a millimeter per second. At that speed, a single electron would need close to 3 hours just to crawl the length of that 1 meter cable. And yet your phone goes from empty to full in under an hour. So where is the energy actually coming from if the electrons carrying it haven't even finished crossing the cable by the time the job is done? That single contradiction is the crack this entire story falls through. Everything you think you know about electricity, that it's a kind of fluid, that it flows through wires the way water flows through a hose, that electrons are the delivery trucks hauling energy from the plug to your phone, is built on a picture that cannot survive that one number. Something else is doing the actual delivering, and figuring out what that something is will take us from a Greek philosopher rubbing a piece of fossilized tree resin 26 centuries ago, all the way down to the strangest, most precisely verified theory human beings have ever built. Start with the word itself, because it's a fossil of the very first clue anyone ever found. Around 600 BCE, a philosopher named Thales, living in the Greek city of Miletus, noticed that if you took a piece of amber, the Greeks called it Electron, and rubbed it briskly against fur or wool, it would afterward pull small, light objects toward it. Bits of straw, dried leaves, feathers. They would leap up off the table and cling to the amber as though something invisible had reached out and grabbed them. Thales had no framework for explaining this. Nobody did for the better part of 2,000 years. It sat in the category of curiosities, a party trick, filed alongside lodestones that pointed north and eels that could shock a man's hand, unconnected to anything, unexplained by anything. The first real crack in the mystery didn't come until the 1700s, when European experimenters started noticing that this amber effect came in two distinct flavors. Rub glass with silk, and the glass behaves one way. Rub amber with fur, and it behaves the opposite way. Two glass rods, both rubbed with silk, push each other apart. Two amber rods, both rubbed with fur, also push each other apart. But bring a rubbed glass rod near a rubbed amber rod, and they pull toward each other. Something wasn't just electrified or not electrified. There were two different kinds of whatever this was, and they interacted with each other in opposite ways depending on which kind met which. Benjamin Franklin gave this observation its lasting name in the 1740s, calling the two kinds positive and negative, and proposing something far more important than the labels themselves, that whatever this stuff was, it obeyed a strict accounting rule. Rub the glass and the silk together, and if the glass ends up with a surplus, the silk must end up with an exactly matching deficit. Nothing is created, nothing is destroyed. It only ever moves from one place to another, and the books always balance. This turned out to be one of the most ironclad laws in all of physics. Electric charge is conserved without a single documented exception in every experiment ever run, from static shocks on a dry doorknob to collisions inside the most powerful particle accelerators on Earth. But conservation only tells you the rule the stuff follows. It doesn't tell you what the stuff actually is. For that, physics needed another century and a half. And it needed two experiments in particular that are worth sitting with, because they're where the story stops being philosophical guesswork and becomes hard, countable physics. In 1897, a British physicist named J.J. Thomson was investigating a strange glow inside sealed glass tubes, cathode rays produced when a high voltage was applied across two metal plates inside a near vacuum. Nobody agreed on what these rays actually were. Some thought they were a wave in some unknown medium. Thomson suspected they were a stream of particles, and he set out to prove it by bending the rays with electric and magnetic fields and measuring exactly how much they deflected. From that deflection, He could work out the ratio of the particles' charge to their mass, and the number that came back was staggering. Whatever these things were, they were thousands of times lighter than even the lightest known atom, and they carried a real, measurable, negative charge. He'd found a piece of matter smaller than the atom, at a time when atom literally meant the thing that cannot be cut. Thomson called his discovery a corpuscle. Within a decade, the world had settled on a different name, borrowed straight from that ancient Greek word for amber, electron. That gave physics the particle. It took Robert Millikan, working between 1909 and 1913, to prove something even stranger about it, that this particle's charge wasn't just small, it was the smallest unit that exists, with nothing in between. Millikan sprayed a fine mist of oil droplets between two horizontal metal plates, and using a fine X-ray source, he could nudge stray electrons onto the droplets, giving each one a tiny electric charge. Then he'd tune the voltage across the plates until a given droplet hung perfectly suspended in midair, its downward pull from gravity exactly canceled by the upward electric force. From the voltage needed to hold each droplet still, and the droplet's mass, he could calculate exactly how much charge it carried. Droplet after droplet, the answer always came out to a whole number multiple of one single fixed value. Never 1.5 times that value, never 2.7 times, always some clean integer multiple. Charge doesn't come in a smooth, adjustable stream the way you'd pour water from a jug. It comes in indivisible units, and every particle of charge in the observable universe, without exception, carries an integer number of that one unit, the charge of a single electron. So by the early 20th century, the picture had solidified into something you could actually build on. Atoms are not indivisible. They contain a dense, positively charged nucleus surrounded by a swarm of much lighter, negatively charged electrons. In an ordinary solid like copper, most of those electrons are locked tightly to their home atom. But roughly 1 electron per atom is only loosely attached, free to detach and wander through the material, jostled by heat, bumping constantly into the vibrating lattice of atoms around it. In a piece of copper wire about as thick as a pencil, there are something on the order of tens of billions of trillions of these free wandering electrons in every single centimeter of length. That is not a shortage. If anything, it's an ocean. And here is where the everyday intuition about electricity as flowing water starts to go badly wrong, because that ocean of electrons is already moving all the time, whether or not any current is flowing at all. At room temperature, each of those free electrons is careening around at roughly 1,000,000 meters per second, colliding with vibrating atoms, ricocheting off in a new random direction, colliding again, a chaotic blur of motion happening trillions of times a second. But it's random. For every electron shooting left, there's statistically another shooting right. The crowd, taken as a whole, goes nowhere. Picture a packed subway platform at rush hour. Everyone moving fast, nobody standing still, and yet the crowd as a mass isn't drifting anywhere in particular. Connect a battery to the wire, and what changes isn't that the electrons start moving. They were already screaming around at 1,000,000 meters a second. What changes is that a faint, persistent electric field appears along the wire's length, and it gives every one of those chaotically moving electrons a tiny, shared nudge in one particular direction. The random sprinting continues completely unaffected. Layered on top of it, almost imperceptibly, is a slow collective drift. And that drift, that organized whisper of net motion buried inside an ocean of chaos, is what we call electric current. Now, for the number that should genuinely unsettle you, measure that drift velocity directly in a typical current-carrying household wire, and it comes out to somewhere around 1/10 of a millimeter per second. A garden snail, one of the slowest creatures most people will ever watch move, covers roughly 10 millimeters per second. That means the electrons supposedly delivering power to your lamp are drifting on the order of 100 times slower than a snail. If you could paint one particular electron a bright color right at the switch the instant you flip it, and then wait for that same electron to physically arrive at the light bulb 3 meters away, you would be waiting the better part of a day. Not a fraction of a second, hours. But the light comes on the instant you flip the switch. No delay a human being could perceive. So if the electrons aren't racing over to deliver the goods, something else is doing the actual work, and it's arriving fast enough that the gap between flipping the switch and the room going bright is, for all practical purposes, 0. Picture a length of pipe packed edge to edge with marbles, with no gaps between them at all. Push one new marble in at one end, and a marble pops out the other end almost immediately. Not because your marble sprinted the whole length of the pipe, but because it nudged its neighbor, which nudged the next one, and so on down the line in a chain reaction that reaches the far end almost instantly, while any single marble barely moved at all. Something structurally similar happens the instant you close a switch. The wire is already packed end to end with free electrons, and closing the circuit doesn't summon electrons from the power source to go running down the wire one by one. It establishes a change everywhere along the wire's length at once, and that change propagates at a speed vastly greater than any individual electron's own crawl. But the marble analogy has a hard limit, and it's exactly where the real physics gets interesting, because in the marble pipe, the energy really is being handed off marble to marble through direct physical contact all the way down the line. That is not what's happening in a wire. The energy is not passed electron to electron through the metal. It travels somewhere else entirely, through the empty space around the wire. And the wire's real job isn't to carry that energy the way a pipe carries water. It's closer to a rail or a riverbank, something that shapes where an entirely different kind of traveler is allowed to go. That traveler is the electromagnetic field, and understanding what it actually is and why almost nobody's mental picture of electricity includes it at all is where the mystery of your phone's charging cable finally starts to resolve. For most of scientific history, forces were assumed to require contact. You push a cart by touching it, you throw a ball by gripping it and letting go. So when two charged objects, separated by open, empty air, were found to pull or push on each other with no visible connection between them, it offended the deepest intuitions of the era's best minds. Newton himself, wrestling with the identical problem for gravity a century earlier, called the idea of one body acting on another across a true vacuum with nothing in between to carry the influence so great an absurdity that he couldn't imagine any competent thinker accepting it, and then admitted he had no better explanation to offer, and moved on regardless. Michael Faraday, a self-taught bookbinder's apprentice who talked his way into a position at London's Royal Institution through sheer persistence and an appetite for every science lecture he could attend for free, refused to let the question drop the way Newton had. Faraday couldn't do advanced mathematics, a genuine limitation that the mathematically trained physicists of his era never let him forget. But he thought in vivid physical pictures, and the picture he developed was this. Every charged object, he proposed, is surrounded by real, physical lines of force radiating outward through the space around it, filling that space the way heat fills a warmed room. When a second charged object enters that space, it isn't being reached across an empty gap by the first object at all. It's simply responding locally to the lines of force already sitting in the space it now occupies. The force isn't transmitted instantly across the void. It's transmitted locally, region by tiny region, through something that actually occupies the space in between. Most of Faraday's contemporaries treated this as an appealing but unrigorous mental crutch, useful for visualization, unnecessary for the actual mathematics, which worked perfectly well treating charges as reaching across empty space with no intermediary at all. It took a young Scottish mathematical physicist named James Clerk Maxwell to take Faraday's stubborn intuition seriously enough to translate it into equations. And in doing so, Maxwell didn't just vindicate Faraday. He uncovered something Faraday himself never could have derived. Working through the 1850s and 1860s, Maxwell distilled the behavior of electric and magnetic fields into 4 compact equations, still taught to every physics student on Earth, in essentially the form he left them. Along the way, he noticed a symmetry that seemed to be missing a piece. Faraday had already shown that a changing magnetic field creates an electric field. Maxwell's equations demanded, purely from internal mathematical consistency, that the reverse also be true, that a changing electric field ought to create a magnetic field, even though nobody had ever measured any such effect. When Maxwell worked out what happens if you let this newly completed pair of effects feed each other, a changing electric field spawning a magnetic field, which spawns another changing electric field, endlessly regenerating each other as they go, the mathematics produced something Faraday's static picture of fixed lines of force never could have: a self-sustaining wave. Not a wave that needs a medium to ripple through, the way sound needs air. A wave made of nothing but the fields themselves, propagating through the empty vacuum, needing no substance at all to carry it. And when Maxwell calculated the speed that wave would travel, using nothing but two constants that had already been separately measured in ordinary electricity and magnetism experiments, nothing to do with optics at all, the number that fell out was almost exactly 300,000 kilometers per second, the measured speed of light. Maxwell had not set out to explain what light was. He'd been studying batteries and magnets, but his equations told him, with a certainty that left no honest room for coincidence, that light itself is an electromagnetic wave. The very field Faraday had insisted filled the space around every charge, caught in the act of oscillating. This is the single fact that dismantles the water in a pipe picture of electricity for good, and it's worth stating plainly rather than working up to gently. The field is not a supporting character in this story. It is where the energy actually lives. In 1884, a British physicist named John Henry Poynting worked out precisely how to calculate the direction and rate at which electromagnetic energy flows through space at any given point, using a quantity now called the Poynting vector. Apply it to something as ordinary as a battery wired to a light bulb, and the result contradicts almost everyone's instinctive mental model. The energy doesn't crawl down the inside of the copper from the battery to the bulb. It streams outward from the battery into the surrounding space the instant the circuit closes, guided by the geometry the wires happen to trace out, flowing through the air and the empty space around the conductors, and only converging inward, funneling into the bulb's filament from all sides at the very last step, where it's finally absorbed and converted into heat and light. The wire's actual job in this picture isn't to be a pipe. It's to be scaffolding. It shapes the field into the correct geometry so the energy knows where to go, the same way a riverbank doesn't carry the water itself, but determines the only path the water is free to take. Even the ordinary warmth you feel from a wire carrying current fits this picture, rather than contradicting it. That heat isn't energy that traveled the length of the wire from one end to the other and finally dumped its load. It's energy flowing in from the surrounding field, absorbed at the wire's surface as the field slightly penetrates the metal, converted there into the random jostling of atoms that we register as heat. The field delivers. The wire absorbs, guides, and occasionally dissipates. It was never the thing doing the carrying. Once you know to look for this, the answer to the puzzle we opened with becomes almost embarrassingly clean. Closing your phone charger circuit doesn't dispatch electrons on a journey down the cable. It establishes an electromagnetic field along the entire length of that cable at once, a signal that propagates at a meaningful fraction of the speed of light, arriving essentially instantly by any measure a human being could perceive. That field then spends the next however many minutes steadily funneling real, usable energy into your battery from the space around the cable, while the electrons inside the copper itself are still, even after the whole charge is finished, nowhere close to having physically crossed that 1 meter of wire. The energy was never waiting on them. It never needed them to arrive anywhere. It needed the field, and the field was already there before you'd even finish pressing the plug into the socket. This same principle is the reason the electrical grid works at all across entire continents, and it's a lesson the engineers of the 19th century learned the hard way through a very public, very expensive failure. The first transatlantic telegraph cable, laid across the ocean floor in 1858, worked for less than a month before degrading into unreadable garbage. Signals that should have arrived as crisp dots and dashes instead smeared into long, indistinguishable blurs, dragging transmission speeds down to a crawl. A bitter scientific dispute broke out over why. William Thomson, later Lord Kelvin, initially pictured the signal traveling down the cable the way water moves through a long, flexible tube, sluggish and diffusing as it went. Others, including the largely self-taught Oliver Heaviside, argued the real culprit, and the real mechanism of transmission in the first place, was the electromagnetic field surrounding the cable, not anything moving through the copper core itself. It turned out the cable's designers had unintentionally sabotaged their own project. To protect the copper conductor, they'd wrapped it in iron armor for strength, and that iron, being a strong conductor itself, badly distorted the surrounding field's geometry, dramatically increasing the cable's capacitance and smearing the signal into mush. It's the reason modern high-voltage power lines run high overhead on tall towers rather than lying on or under the ground. Even damp earth conducts well enough to interfere with the field's geometry, so engineers deliberately insert a wide gap of insulating air between the wire and the ground to keep that field clean. None of this changes when you switch from a battery's steady, direct current to the alternating current running through the actual power grid, and this is worth being precise about because it resolves a question that trips people up the moment they first hear that current in AC wiring never travels anywhere at all. The electrons inside the wire are simply wiggling back and forth 60 times a second, gaining no net ground in either direction across a full cycle. If the electrons themselves are only oscillating in place, how does energy manage to travel outward across an entire continent, from a power station to a wall socket hundreds of kilometers away? The answer is the same field mechanism, just running on a clock. Every half cycle, the direction of the current in the wire flips, but the electric field and the magnetic field flip together, in lockstep and their cross product. The very quantity the Poynting vector measures, the direction energy is actually flowing, points the same way regardless of which half of the cycle you happen to catch it in. The energy flux never reverses, even though the current that's generating it reverses twice every cycle. The field carries the power continuously and in one direction, from generating station to your wall outlet, while the electrons themselves are, in an important physical sense, going absolutely nowhere. None of what's been laid out so far, the field, the Poynting vector, Maxwell's wave equation, the whole classical picture, is wrong exactly, but it is incomplete in a specific and important way because it still leaves one very ordinary question dangling. Why does copper let electrons drift so freely while a piece of window glass, subjected to the exact same voltage, refuses to carry any current at all? The classical picture of fields and charges has no answer for that question because the answer isn't hiding in the field. It's hiding inside the atoms of the material itself. And finding it means leaving classical physics behind completely and going down into quantum mechanics, down to the scale where electrons stop behaving like tiny orbiting planets and start behaving like something almost nobody's everyday intuition has ever had to grapple with. The picture of an electron as a tiny ball tracing a neat circular orbit around a nucleus, the one still printed on classroom posters and company logos, is not a simplification of the truth. It's simply wrong in a way that matters here. Quantum mechanics, developed through the 1920s, replaced that orbiting ball picture with something far stranger. Each electron in an atom exists as a wave function, a mathematical description of the probability of finding it in any given location, spread out as a cloud rather than pinned to a single trajectory. These clouds only come in certain specific allowed shapes, and each shape corresponds to one specific fixed energy. Not a continuous range of energies the electron could tune itself to at will, but a strict ladder of discrete, separated rungs with genuinely nothing physically possible in between. In a single isolated atom, sitting alone with nothing nearby to interact with, these energy rungs are sharp and widely spaced, cleanly separated from each other. But no atom in an ordinary solid object is ever isolated. Pack roughly 100 billion trillion atoms together into a single cubic centimeter of metal spaced only a few tenths of a nanometer apart, and the electron clouds of neighboring atoms start to overlap and interact. Each of those trillions upon trillions of formerly identical, sharply defined energy rungs splits, ever so slightly, into a separate rung for every atom involved. And with that, many atoms crammed together, Those slightly shifted rungs pack so closely that they blur into what is, for all practical purposes, a continuous band of allowed energies. What was a single sharp line in one lone atom becomes a broad, smeared-out band in a solid. And critically, the gap that used to separate one sharp energy level cleanly from the next also survives the transition. Except now it's a gap between two entire bands rather than between two single lines. This band structure, and nothing else, is the actual answer to why copper conducts and glass doesn't. But getting there requires one more piece of quantum machinery, arguably the single most consequential rule in all of solid-state physics. The Pauli exclusion principle, formulated by the Austrian physicist Wolfgang Pauli in 1925. It states, with no known exceptions, that no two electrons anywhere in a system can occupy the exact same quantum state at the same time. Every energy rung can hold at most two electrons, one spinning one way, one spinning the other. And once both of those slots are filled, that rung is closed. Any further electron has to find a different, unoccupied rung, no matter how energetically similar the nearby rungs might seem. Now, imagine filling up a solid's energy bands with all of its available electrons, starting from the lowest energy and working upward, respecting that strict 2 per rung rule the entire way. In a metal like copper or aluminum, the highest band that ends up holding any electrons is left only partially full. There are electrons occupying it, but there's also plenty of unoccupied room left in that very same band, at energies barely above where the last electron landed. Apply even a faint electric field, and those electrons have somewhere to go, a nearby, easily reachable, empty state to shift into, requiring only a whisper of extra energy. The door is standing wide open. That ease of movement, that abundance of adjacent empty rungs right next to the occupied ones, is what a conductor actually is at the quantum level. Glass and insulators generally land in the opposite situation entirely. Their highest occupied band, the valence band, turns out to be completely, perfectly full, with not a single unoccupied rung left anywhere inside it, thanks to the exclusion principle locking every slot. The next available band sits well above it, separated by a substantial energy gap, in diamond, for instance, roughly 5.5 electron volts, a genuinely enormous distance at the atomic scale. An ordinary household voltage doesn't come remotely close to supplying enough energy to boost an electron across a gap that wide. The electrons aren't chained in place by anything mechanical. They're locked in by pure quantum bookkeeping. Every seat in their own band is already taken, and the next available seating section is too far away to reach. Apply a field, and there is genuinely nowhere for the electrons to go, so nothing moves and no current flows, no matter how long you wait or how hard you push. Semiconductors, silicon, germanium, the entire foundation of every microchip ever manufactured, sit in the narrow, useful gap between these two extremes. Their valence band is also completely full, and their conduction band also empty, structurally identical to an insulator in that respect, but the gap separating the two is dramatically smaller, about 1.1 electron volts in silicon versus that roughly 5.5 electron volt gulf in diamond. That difference sounds modest on paper, but it changes everything practically, because at ordinary room temperature, the constant random thermal jostling of the crystal lattice is occasionally violent enough to kick a lucky electron clear across that narrower gap and into the conduction band, where it's suddenly as mobile as any electron in a metal. And the empty seat that electron left behind in the valence band, physicists call it a hole, behaves in every practical sense like its own separate positively charged particle, capable of appearing to drift through the material as neighboring electrons hop one by one into the vacancy, passing the emptiness along like a bubble rising through water. Deliberately introduce trace impurity atoms into that silicon lattice, a technique called doping, and you gain precise engineered control over how many mobile electrons or mobile holes the material carries. Add atoms that bring along one extra electron each, and you create a surplus of easily excited electrons ready to jump into the conduction band, a material dominated by negative charge carriers. Add atoms that are one electron short instead, and you create a corresponding surplus of holes, mobile positive charge carriers. Every transistor, every diode, every processor and memory chip and solar cell ever built is nothing more than carefully engineered regions of these two flavors, arranged and layered against each other with extraordinary precision. The entire digital world, quite literally, runs on the width of that one energy gap in silicon and on how deliberately it can be widened or narrowed with a scattering of the right foreign atoms. There's a further layer to the quantum story worth pausing on because it resolves something the classical field picture leaves completely unexplained. Why does a wire heat up and resist current in the first place? In a perfectly regular crystal lattice, atoms sitting in flawless, unbroken, repeating rows with absolutely nothing out of place, the physicist Felix Bloch showed in the late 1920s that a conduction electron's wave function actually fits the periodic pattern of that lattice so cleanly that it experiences no scattering whatsoever. In a truly perfect crystal, current would flow forever with zero resistance, requiring no continuous push at all once it got started, the same way a ball would roll forever across a perfectly flat, perfectly frictionless surface. Real crystals are never perfect, and that imperfection is where resistance actually comes from, not as some intrinsic property electricity always carries with it, but as a direct physical consequence of things going wrong inside the lattice. Above absolute zero, every atom in the crystal is constantly vibrating in place, and those vibrations come in their own quantized packets, called phonons, the vibrational equivalent of a photon, a quantum of sound rather than a quantum of light. A conduction electron drifting through the lattice regularly collides with these phonons, gets deflected off its course, and loses a little of its organized, forward-drifting motion with every collision, converting it into the random background jostling of the lattice, which is to say, into heat. Impurity atoms scattered through the metal, grain boundaries where microscopic crystal domains meet at odd angles, missing atoms, and other structural defects all contribute their own additional scattering on top of that. Every one of these mechanisms chips away at the electron's organized drift and hands the lost energy over to the lattice as heat. This is the real physical origin of electrical resistance, not friction in any mechanical sense, but a running tally of quantum collisions between a drifting electron wave and every imperfection standing in its path. And this is exactly why one particular discovery, made in a Dutch laboratory in 1911, counts among the strangest and most genuinely mind-bending results in the whole history of physics. Heikki Kamerlingh-Onnes had recently succeeded in liquefying helium, opening up access to temperatures within a few degrees of absolute zero for the first time in history, and he used that new capability to measure the electrical resistance of mercury as he cooled it down step by step. Below about 4.2 Kelvin, the resistance didn't gradually fade towards some very small number, the way you might expect from a picture where cold simply calms the lattice's vibrations and quiets phonon scattering down. It dropped, abruptly and completely, to exactly zero. Not a number too small to easily measure, genuinely, precisely, unmeasurably zero, confirmed by starting a current flowing in a closed superconducting loop and then simply watching it for months, for years, with absolutely no detectable decay whatsoever. A current with nothing pushing it, coasting forever. The explanation took nearly half a century to arrive, published in 1957 by John Bardeen, Leon Cooper, and Robert Schrieffer in what's now called BCS theory, and it earned all three a Nobel Prize. Below a material-specific critical temperature, individual conduction electrons, which ordinarily repel each other fiercely, sharing the same negative charge, begin instead to pair up. The mechanism is genuinely counterintuitive. One electron moving through the lattice tugs the nearby positively charged atomic nuclei very slightly inward toward itself as it passes, and that momentary faint surplus of positive charge is enough to attract a second electron toward the same region, even though the two electrons involved can be separated by hundreds of atomic spacings and never come remotely close to touching. This bound pair, called a Cooper pair, has an entirely different quantum character from a lone electron. While single electrons are fermions, bound by the Pauli exclusion principle to never share a state with another, a Cooper pair behaves instead as a boson. And unlike fermions, an unlimited number of bosons are perfectly free to pile into the exact same quantum state simultaneously. Below the critical temperature, an enormous number of these pairs condense together into one single, shared quantum state spanning the entire material. And scattering one single pair out of that state would require breaking it apart entirely, at an energy cost the surrounding cold lattice simply cannot supply. With no viable path to scatter, the pairs glide through the material as one unified quantum entity, immune to the very imperfections that create ordinary resistance, and the current flows forever. For 3/4 of a century after Kamerlingh Onnes's discovery, this remained a laboratory curiosity, confined to temperatures within a hair's breadth of absolute zero and demanding scarce, expensive liquid helium to reach. Until 1986, when two IBM researchers in Zurich, Georg Bednortz and Alex Muller, found superconductivity in an unassuming ceramic compound at a startling 35 Kelvin, several times higher than any previous record. Within a single year, other researchers had pushed a related ceramic compound known by the shorthand YbCO past 90 Kelvin, crossing a genuinely practical threshold, because that's above the boiling point of liquid nitrogen, a coolant so cheap and so easy to produce that it's practically an industrial commodity by comparison to liquid helium. And here is the part that makes the story properly unresolved rather than merely historical. Nobody fully knows why these particular ceramics superconduct. The conventional phonon-mediated Cooper pairing that explains ordinary metals doesn't cleanly account for what's happening inside them. Physicists know the electrons are pairing up. They know those pairs are condensing into a single collective quantum state, exactly as BCS theory would predict for an ordinary superconductor. What they don't yet know, after nearly 40 years of research by thousands of physicists worldwide, is what mechanism is actually gluing those particular pairs together. It remains one of the genuinely open problems at the center of condensed matter physics, and the eventual answer, if it arrives, is one of the most plausible candidate routes to a material that could someday superconduct at ordinary room temperature, at which point power grids, maglev trains, and computer processors would all become almost unrecognizably different from what they are today. There's still one layer left beneath all of this, and it's the one that finally answers, at the deepest level physics currently reaches, what electricity actually is rather than merely how it behaves. Because everything covered so far, Maxwell's field, the Poynting vector, even the quantum band structure of a crystal, still treats the electromagnetic field itself as a smooth, continuous, classical backdrop. It isn't one. The field is quantized, exactly the way charge itself turned out to be quantized in Millikan's oil drop experiment a century ago. And the theory that describes this, quantum electrodynamics, universally shortened to QED, stands as the single most rigorously tested scientific theory that has ever existed. The clue that the field itself might be discrete first surfaced in 1900 when Max Planck found that he could only make his equations for the light radiating off a hot object match reality by assuming that energy at a given frequency is exchanged in fixed, indivisible packets rather than smoothly. Planck himself treated this as a mathematical trick rather than physical truth, and spent years afterward trying to find a way around it. 5 years later, in the same extraordinary stretch that also produced special relativity, Albert Einstein took the packets seriously as physically real, and used the idea to explain the photoelectric effect, why shining dim, high-frequency light on a metal surface knocks electrons loose instantly, while flooding the same surface with intense, low-frequency light does absolutely nothing at all, no matter how long you wait. Light itself, Einstein proposed, arrives as discrete particles, each one carrying an amount of energy fixed entirely by its frequency. These particles later acquired the name we use today, photons. Quantum field theory, developed through the 1920s, 30s, and 40s, eventually resolved this into a single, unified picture that applies to every particle in nature, not just light. The truly fundamental objects aren't particles at all. They're fields, invisible entities that fill the whole of space, existing everywhere at every moment, whether disturbed or not. There is an electromagnetic field. There is a separate field for electrons. What we experience and detect as a particle is simply a quantized ripple, a minimal possible disturbance in its corresponding field. A photon is the smallest possible excitation of the electromagnetic field. An electron is the smallest possible excitation of the electron field. Fields are the fundamental substrate. Particles are what a disturbance in that substrate looks like from the outside. Quantum electrodynamics, developed independently and then shown to be equivalent by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the late 1940s, describes precisely how the electron field and the electromagnetic field interact. And remarkably, the entire theory reduces to just one single fundamental event, repeated over and over in every conceivable combination. An electron emits or absorbs a photon. That's the whole vocabulary. Every spark, every bolt of lightning, every chemical bond holding every molecule together, every signal racing down every nerve in your body, and yes, every electric current in every wire on Earth is built entirely from that one interaction, endlessly repeated and combined. When two electrons repel each other, in this picture, they aren't reaching across empty space through some unexplained action at a distance, the way Newton feared and Coulomb's law simply assumed. They're exchanging what physicists call virtual photons. A quantum of the electromagnetic field passed directly between them, carrying momentum from one to the other, the physical mechanism underneath the abstract force Coulomb had only been able to measure and describe mathematically a century and a half earlier. These virtual photons are meaningfully different from the real photons streaming out of a light bulb or arriving from a distant star. They exist only for the fleeting duration of a single interaction. They cannot be captured by any detector, and they never travel independently through space the way ordinary light does. They are, in a real sense, the field caught in the very act of transmitting force, rather than a free traveler in their own right. This framework's predictive precision is difficult to convey honestly without sounding like exaggeration, so it's worth being exact about it. Every electron behaves like an extremely small magnet, and the strength of that magnetism is captured by a single number physicists call the electron's Joule factor. The simplest version of quantum theory predicts this number should land at exactly 2. QED refines that prediction by accounting for the fact that an electron is never truly isolated. It's constantly surrounded by a shimmering, ever-present cloud of virtual photons flickering into brief existence and vanishing again, subtly nudging its properties. Fold that correction into the calculation, and QED's prediction for the electron's G factor matches the best laboratory measurement to better than 1 part in a trillion. To put a number that abstract into something graspable, it's roughly equivalent to measuring the distance from New York to Los Angeles and having your figure come out accurate to within the width of a single human hair. Nothing else in the whole of experimental science has ever been checked against theory with anything close to that level of agreement. QED also forces a strange revision of what empty space even means, and this revision isn't a purely theoretical curiosity. It has been measured directly, more than once. Because every field is subject to Heisenberg's uncertainty principle, none of them are ever permitted to sit perfectly, silently still, not even in a region containing no charge, no matter, and no radiation whatsoever. The electromagnetic field in a true vacuum is constantly, restlessly fluctuating, briefly conjuring virtual photons into fleeting existence before they vanish again. In 1948, the physicist Hendrik Casimir predicted a direct physical consequence of exactly this. Place two completely uncharged ordinary metal plates extremely close together in a vacuum, and the tight gap between them restricts which wavelengths of these vacuum fluctuations are able to fit, while outside the plates, in the open space around them, every possible wavelength remains free to exist. That imbalance produces a real, measurable pressure pushing the two plates toward each other, arising from nothing but the restless quantum churn of what looks, by every classical measure, like perfectly empty space. This effect has since been measured directly in laboratories, confirming that the vacuum itself is not nothing. It's a living quantum landscape, and its restlessness leaves fingerprints you can weigh. So gather every piece of this together, because the honest, complete answer to what electricity actually is turns out to be built from every layer we've walked through, not any single one of them in isolation. Electricity is not a substance. It has no independent existence as a fluid or a spark or a stream of anything flowing steadily from one place to another. It is the name given to an entire coordinated quantum process, charged particles, overwhelmingly electrons in ordinary matter, arranged by the Pauli exclusion principle into the specific energy bands a material's crystal structure allows, shifting collectively among the available states in response to a field established almost instantly throughout an entire circuit. That field itself is a quantized entity. Its own excitations are photons, and force between any two charges is ultimately nothing more or less than a continuous exchange of those photons, virtual and fleeting, back and forth between them. Resistance is what happens when that organized collective drift scatters off imperfections in a real, imperfect lattice, converting a little of the electron's shared motion into the random background jostle of heat at every single collision. And under exactly the right conditions, that scattering can be suppressed almost entirely, letting a current flow forever with no push at all, as a single unified quantum state gliding untouched through a lattice that no longer has any power to slow it down. None of that changes the number this entire journey began with. Your phone's charging cable is still about a meter long. The electrons inside it are still drifting at a pace slower than a garden snail, still nowhere close to physically finishing that 1 meter crossing by the time your battery reads full. What actually filled that battery was never the electrons themselves making the trip. It was the field, established across the entire length of the cable in a fraction of a second, carrying real, usable energy inward from the space surrounding the wire, the whole time your phone sat charging on the nightstand, delivering everything it needed to deliver long before a single electron could have covered the distance a human eye can see in a single glance. There's a piece missing from everything covered so far, and it's one most people walk past without ever noticing the gap. Where does the field pushing all of this actually come from in the first place? A wire full of free electrons and a well-understood crystal structure explains how current moves once it's started. It says nothing about what starts it. For that, the story has to go back to 1800 to an Italian physicist named Alessandro Volta, and to a genuinely strange piece of gossip about frog legs that had been circulating in scientific circles for about a decade before he got involved. Volta's colleague, Luigi Galvani, had noticed that a dissected frog's leg would twitch violently when touched simultaneously by two different metals. And Galvani, reasonably enough given what was known at the time, concluded he'd discovered a form of animal electricity generated by living tissue itself, a life force stored inside the muscle. Volta suspected something else entirely, that the frog's leg wasn't generating anything at all. It was simply acting as a moist conductive detector, responding to something the two different metals themselves were producing between them. To prove it, Volta built a device that needed no living tissue whatsoever, alternating discs of two different metals, zinc and copper, separated by cloth soaked in salt water, stacked one on top of another into a column. This voltaic pile, assembled in 1800, was the first genuine battery in human history, and it produced a steady, continuous electric current with nothing biological involved at all. What Volta had actually discovered, though he didn't yet have the atomic-level vocabulary to describe it this way, is that different metals hold onto their electrons with different strengths, a property that would later be understood in terms of each metal's characteristic willingness to give up or accept electrons in a chemical reaction. Zinc atoms are relatively eager to shed electrons and dissolve into the surrounding salt solution as positive zinc ions. Copper is comparatively reluctant to do the same. Stack the two metals with a salt-soaked conductor between them, and zinc atoms at one electrode begin steadily giving up electrons and dissolving into solution, while at the copper electrode, a separate chemical reaction consumes electrons arriving from the external circuit. The zinc electrode ends up with a persistent surplus of electrons relative to the copper electrode. And that persistent charge imbalance is precisely what creates the steady electric field driving current around an external circuit the moment you connect one. This is, at bottom, Exactly what every battery on Earth still does today. Whether it's an old-fashioned voltaic pile, an alkaline cell in a television remote, or the lithium-ion pack sitting in the phone that started this whole exploration. Inside every battery, a carefully chosen pair of chemical reactions is running at two separate locations. One that wants to release electrons, one that wants to consume them, kept physically apart from each other so that the only path those electrons can take between the two reactions is through whatever external circuit you've connected. The battery isn't a reservoir of electricity waiting to be released, the way a water tank holds a fixed volume of water ready to be drained. It's closer to a chemical engine, continuously converting the energy stored in chemical bonds into a sustained electric field, for exactly as long as the chemical reactants inside it hold out. When a battery dies, nothing about electricity itself has been used up or exhausted. The chemistry has simply run its course. The reactive zinc has fully dissolved, or the chemical species needed at the other electrode have been fully consumed. And without an ongoing chemical reaction to maintain it, the charge imbalance driving the field collapses and the current stops. Lithium-ion batteries, the ones actually charging your phone, work on the identical underlying principle with a more sophisticated arrangement. Lithium ions shuttle back and forth between two different electrode materials, embedding themselves into one material's atomic structure during charging and the others during discharging, while the electrons freed or consumed by that ion movement take the external path through your device, doing useful electrical work along the way. Charging your phone means running this entire reaction in reverse. Using the field arriving through the very cable, this whole story began with to force lithium ions back to the electrode they started from, physically restoring chemical potential energy inside the battery, ready to be released again the next time you unplug it and put the phone to work. For most of the 19th century, this chemical approach, direct current, a steady, one-directional field driven by an ongoing chemical reaction inside a battery, was essentially the only practical way anyone knew how to generate electricity on demand. That started to change once Faraday's 1831 discovery of electromagnetic induction. The finding that a changing magnetic field induces an electric current in a nearby conductor matured from a laboratory curiosity into industrial-scale machinery. Enormous rotating generators, spun by falling water or by steam pressure from burning coal, sweeping magnets past coils of wire fast enough to induce current on a genuinely massive scale, current that reversed direction with every half-turn of the generator's shaft, rather than flowing steadily in one direction the way a battery's did. This was alternating current, and it set off one of the more openly hostile technological rivalries in American industrial history. Thomas Edison had already built his reputation and a substantial business around direct current. His electric lighting systems, his patents, his entire commercial infrastructure were engineered around DC from the ground up. George Westinghouse, backed by the engineering work of Nikola Tesla, bet instead on alternating current, and the deciding factor in what became known as the War of the Currents turned out to hinge on something the field theory covered earlier makes almost obvious in hindsight: distance. Direct current, as generated and distributed in that era, suffered severe energy losses over any meaningfully long transmission distance, forcing power stations to be built within roughly a mile or two of every neighborhood they served. Alternating current had a critical practical advantage that had nothing to do with which type of current was somehow more real. A C voltage can be stepped dramatically up or down using a transformer, a device built from nothing more exotic than two coils of wire wound around a shared iron core with no moving parts, no chemistry, and crucially, no direct electrical connection between its input and output sides at all. A transformer works entirely through Faraday's induction, running in a continuous loop. Alternating current flowing into the first coil creates a constantly changing magnetic field in the shared iron core, and that changing field, reaching the second coil, induces its own current there, with the ratio of the number of turns of wire in each coil determining exactly how the voltage gets scaled up or down between the two sides. Step the voltage from a power plant up to hundreds of thousands of volts for the long haul across a transmission line, and the same total power can be delivered while pushing dramatically less current through the wire. And since resistive losses in a wire scale with the square of the current flowing through it, That trade is an enormous net win, letting power travel hundreds of kilometers with only modest losses along the way. Step the voltage back down again with another transformer once it reaches your neighborhood, and it arrives at a level safe enough to run through household wiring and into your wall socket. Edison's DC systems had no comparably simple, efficient way to do this kind of voltage conversion at the time, and by the early 20th century, AC had decisively won the argument on pure economics, becoming the standard for essentially every electrical grid built anywhere in the world since. There's a broader phenomenon connected to all of this that almost everyone has personally experienced, but rarely connects to any of the physics covered so far, and it's worth pulling in explicitly because it's the single most dramatic natural demonstration of everything already discussed. Lightning. A thunderstorm is, at its core, an enormous, entirely natural version of Franklin's rubbed amber, playing out on a genuinely planetary scale. Inside a developing storm cloud, violent internal updrafts and downdrafts drive collisions between ice crystals and soft, slushy hail pellets called graupel, and those collisions transfer electrons from one to the other in exactly the same basic mechanism as rubbing glass with silk. Smaller ice crystals tend to end up positively charged and get carried upward by the storm's updrafts, while heavier graupel tends to end up negatively charged and sinks toward the base of the cloud. Over the course of the storm, this sorting process can build up a truly staggering charge separation, tens to hundreds of millions of volts of potential difference between the negatively charged cloud base and the ground beneath it, or between oppositely charged regions within the cloud itself. Air is normally an excellent insulator, for exactly the quantum reason discussed earlier. No meaningfully accessible energy states nearby for its electrons to shift into under an ordinary field. But there is no such thing as a perfect insulator when the applied field grows extreme enough, and the field inside and beneath a mature thunderstorm eventually exceeds even air's substantial resistance. A stepped leader. A narrow, initially invisible channel of ionized, briefly conductive air begins working its way downward from the cloud in short, discrete bursts, blazing a rough conductive trail toward the ground. The instant that descending leader connects with an upward-reaching streamer of opposite charge rising to meet it from the ground or from some tall, prominent object below, a complete conductive path snaps into existence between cloud and earth, and an enormous surge of charge floods through it almost instantaneously in what's called the return stroke. The visible, blindingly bright flash of lightning, carrying on the order of tens of thousands of amperes, briefly heating the surrounding air to somewhere around 30,000 Kelvin, roughly 5 times hotter than the surface of the sun. That explosive heating causes the air along the channel to expand violently and then contract just as fast, generating the pressure wave you hear seconds later as thunder. It is, from first principle to final flash, the exact same physics as a spark leaping off a doorknob after you've shuffled across a carpet in dry winter air. Franklin's original observation about charge imbalance and conservation scaled up from a barely perceptible static crackle to a 100 million volt discharge visible from kilometers away. There's one more application of this entire body of physics worth walking through carefully because it runs directly through your own body at this very moment, and it closes the loop on why any of this should matter to you personally rather than remaining an abstract curiosity about wires and batteries. Every thought passing through your mind right now, every heartbeat keeping you alive, every muscle contraction moving your eyes across these words, is fundamentally an electrical event. Not electricity in the metaphorical, loose sense the word often gets used in casually, but the literal same physics of charge, field, and current worked through so far, running on an entirely different kind of conductor. A living cell membrane. Every neuron in your nervous system maintains a small but very real voltage across its outer membrane, typically around 70 millivolts, negative on the inside relative to the outside, maintained continuously by specialized proteins embedded in the membrane, molecular pumps that spend a steady supply of chemical energy actively hauling sodium ions out of the cell and potassium ions in, working against the ion's own natural tendency to diffuse the opposite way, keeping the cell's interior charge reliably different from its surroundings at every moment the neuron is alive. When a neuron fires, a coordinated cascade of specialized ion channels in the membrane snaps open in rapid sequence, and positively charged sodium ions flood inward, briefly and dramatically reversing the local voltage across that small patch of membrane. That local reversal, in turn, triggers the identical channels immediately next door to open as well, and the reversal propagates down the length of the neuron as a fast-moving wave. This is what a nerve impulse and action potential physically is. Not electrons drifting through a wire in the metallic sense, but a traveling wave of ions crossing a membrane through precisely timed protein channels, executing the exact same underlying logic of charge, field, and current that's been the subject of this entire exploration, just running on ions instead of electrons, and on a lipid membrane instead of a copper lattice. Your heart runs on the identical principle, orchestrated by a small cluster of specialized pacemaker cells that spontaneously and rhythmically fire this exact same kind of electrical signal roughly once a second at rest, and that signal then propagates outward through the heart's own specialized conducting tissue, triggering the precisely coordinated muscular contraction that pumps blood through your entire circulatory system. An electrocardiogram, the familiar spiky trace hospitals record from small electrodes stuck to a patient's skin, is quite literally measuring these traveling ion currents directly from outside the body, using nothing more exotic than the same electromagnetic field principles already covered. Voltage differences created by moving charge, detected without any wire ever needing to touch the actual source. This relationship between voltage and current is also the exact reason a common piece of intuition about electrical danger gets things backward. And it's worth correcting explicitly because it matters in a very literal, practical sense. People often assume high voltage is inherently what makes something lethal, and it's genuinely true that a static shock from shuffling across a carpet in dry winter air can involve tens of thousands of volts. And yet, it's utterly harmless, felt as nothing worse than a brief, unpleasant snap. What actually determines danger to a human body is current, not voltage on its own, because it's current, the actual rate of charge flow through tissue, that can disrupt the delicate electrical signaling running your heart's own pacemaker cells, the same electrical mechanism described a moment ago. A static shock delivers an enormous voltage, but only an infinitesimally tiny total quantity of charge over a duration measured in a fraction of a millisecond, and the human body's electrical resistance, typically somewhere in the range of a few hundred to a few thousand ohms, depending heavily on how damp your skin happens to be at the time, is more than enough to keep the resulting current vanishingly small. A wall socket, by contrast, is a far lower voltage than a static shock, but it's backed by a power station capable of sustaining that voltage indefinitely, willing and able to push as much current through any conductive path, including a human body, as that path's resistance will permit, for as long as the circuit stays closed. It's not the size of the push that determines the outcome. It's how much charge that push manages to move through you, and for how long. This is also, incidentally, the actual physical reasoning behind a piece of electrical safety equipment most people have installed in their homes without ever fully understanding why it works: the ground wire, and the wider practice of electrical grounding generally. Connecting a circuit's chassis or casing to the actual earth, literally a metal rod driven into the ground outside your house, provides an enormous, effectively bottomless reservoir capable of absorbing or supplying charge without its own potential shifting in any meaningful way, precisely because the Earth itself is so vastly larger than any household circuit that could conceivably be connected to it. If a fault develops inside an appliance, and its metal casing becomes unintentionally connected to a live wire, a properly grounded system gives that stray, dangerous current an easy, low-resistance path straight to Earth instead of through whichever person happens to touch the appliance next. And that surge of current flowing through the ground wire is exactly what trips a circuit breaker, which is itself nothing more exotic than a device that detects a current well beyond its rated safe level and physically breaks the circuit's continuity before real damage or injury can occur. There's one further, closely related phenomenon worth walking through, because it explains something genuinely counterintuitive about how electric fields behave around conductors, and it connects directly back to Faraday's original insight about lines of force filling space. If you place a hollow closed conductor, a metal box, a length of wire mesh, even something as ordinary as a car's outer metal shell, around a region of space, and then apply an external electric field to that whole arrangement, something remarkable happens on the inside. The field inside the enclosed cavity drops to essentially zero, regardless of how strong the external field pushing on the outside happens to be. This is called a Faraday cage, named for the same physicist who first correctly intuited the whole concept of the field nearly 2 centuries ago. And the mechanism behind it is a direct, elegant consequence of the fact that a conductor is, by definition, packed with free charges able to move in response to any field at all. The moment an external field is applied, those free charges in the conducting shell instantly rearrange themselves across the surface, accumulating in exactly the right pattern to generate their own internal field that precisely and completely cancels the external field everywhere inside the enclosed cavity. It's the identical free electron behavior described earlier in an ordinary current-carrying wire, just redirected toward a different outcome. Instead of drifting steadily in one direction to carry a current, the electrons in a Faraday cage's shell simply redistribute themselves once into a static configuration and then sit still, having already done their job of neutralizing the field inside completely. This is why the interior of a car is one of the statistically safer places to be during a lightning strike. It isn't the rubber tires insulating the occupants from the ground, as popular belief often assumes, but the metal shell of the car body itself, acting as a Faraday cage and routing the enormous surge of current around the outside of the vehicle rather than through the empty air inside it. Every one of these practical phenomena, the danger genuinely lying in current rather than voltage, the way a grounded wire gives a fault current somewhere safe to go, the way a metal shell can cancel an external field completely inside its own hollow interior, traces back to the exact same physical picture built up across this entire exploration. Free charges arranged by quantum mechanics into whichever states a given material structure allows, responding almost instantly to whatever field happens to be present, whether that field arrives from a battery's chemistry, from a spinning generator hundreds of kilometers away, from the violent charge separation inside a thunderstorm, or from the ordinary static buildup of shuffling across a carpet on a dry afternoon. So return one final time to the number that opened this entire journey. A 1-meter cable, electrons inside it drifting at roughly 1/10 of a millimeter per second, slower than a garden snail, needing the better part of a day to physically cross that single meter of copper, and a phone battery that fills completely in well under an hour regardless. There was never a contradiction here, only a gap in the picture most people carry around without ever examining it. The electrons were never the delivery mechanism. They never needed to be. The instant that cable circuit closed, an electromagnetic field established itself along its entire length in a fraction of a second, and from that moment forward, energy streamed inward from the space surrounding the wire itself, not from electrons completing a slow crawl from one end to the other, but from the same field Faraday first pictured as invisible lines of force filling empty space, and that Maxwell proved, with 4 equations and a number that turned out to be the speed of light, was never empty at all.